were going to work, I guess, on the start of Chapter 2. School hasn't started back up yet again, so I haven't gotten any new materials, but, or not to Chapter 4. But Chapter 4 is where we're going to start, so I figured that would be a good place.
Okay. What kind of stuff is in Chapter 4?
Chapter 4, I believe, where did I set my textbook at? I believe it's the start of integration.
Integration, okay. So there's lots of different ways that can start. So I need to know what you're working on specifically.
My math book. Looking through my math. Just had it.
Integration is basically the area under the curve. So if I want to know what the area under the curve between those 2 points are, I want to integrate that function from A to B. That'll tell me the area under the curve. And that's the starting point for all integration. Can you be more specific as to where you're beginning?
Just using the textbook. The teacher hasn't given us any materials yet, but I was going to start looking at the textbook at the beginning of Chapter 4.
Okay.
Which I was going to give you what... I know we have similar textbooks, but I was going to give you what my textbook said, but I can't seem to figure out where I set it down at.
Okay.
I thought it was right here on my desk.
What text? You have the textbook that is Calculus by Finney, DeManna, Waits, and Kennedy? No, because their Chapter 4 is not integration.
No, that was,
Let me look at my other textbook. Yeah, my other textbook.
Calculus of a single variable.
Chapter 4 is integration on my other textbook. I have 2 textbooks for calculus.
Mine's the calculus of a single variable by,
By who?
Lawson, Hostella, Edwards.
Okay, that's my calculus book also. I have the 8th edition, and Chapter 4 is where integration begins.
I was just starting to figure we should start there.
Okay. Let me take a look real quickly. Chapter 4. Well, let's talk about a couple things. What's that equal to?
Oh, S of 2x dx. X squared y plus c?
Just x squared plus c. In other words, all we have to do is apply the power rule to that. In reverse of the power rule for differentiation, In other words, when you apply the power rule, you add 1 to the exponent and you divide by the new exponent. So if I add 1 to 2x, it's 2x squared, divide by 2, ends up equaling x squared plus c. Now, the reason we have a plus c is because if we take the derivative of that, we get 2x, regardless of what c is. In other words, when you're taking an indefinite integral, you actually have an infinite number of answers that are all correct.
Yeah.
Remembering that if you take the derivative of a constant, you get 0. So the integral is the antiderivative. Now, it's not really clear. For a long time, back in the 1700s, they actually had 2 different branches of mathematics. One was differential calculus, which was the rate of instantaneous change. In other words, the slope of the tangent line. That's the rate of instantaneous change. You also had a different branch of mathematics that was based on finding the area under the curve. Well, these two things don't appear to have anything to do with one another. The slope of the tangent line and the area under the curve don't seem to have anything to do with one another. But it took about 50, 100 years before Newton realized that one was the inverse of the other. In other words, the integral is the inverse of the derivative, which leads to the fundamental theorem of calculus, which is to say that if you have an integral and you take the derivative of that integral, you get f of x. So that the integral, or I should say the integral is the antiderivative. If you have a function such as x squared divided by 3, and you want to take the integral of that, then you do the opposite of what you would have done with the derivative. You add 1 to the exponent and divide by the new exponent. So that's x cubed over 9. Plus c, and the plus c, obviously if we take the derivative of x cubed over 9 plus c, we're going to get x squared over 3. So finally Newton and Leibniz realized back in the 1700s that the integral was the inverse of the derivative, even though they don't seem to be related. That is the case. So if you take the derivative of the integral, you get the function. Now, here, let me look at this book. All right, let's go through a few of these. What's that equal to?
Integral of
0 dx.
Yeah. 0 dx, that would be 0 plus c, right?
Well, it would just be, yes, 0 plus c. In other words, if you take the derivative of a constant, you get 0. Which means if you take the integral of 0, you get a constant.
Yeah.
What's the integral of k dx where k is a constant?
You then get the constant, or x to the constant plus 1 times divided by the constant, or not times, but divided by the constant.
You get kx to the 1 plus c. In other words, one can look at this as being k times x to the 0th power dx. Add 1 to the exponent, divide by the new exponent, you get kx plus c. Okay, the power rule works great when you can apply it. What's the integral of that?
X to the 5th divided by 5.
Yeah, plus c, exactly. So the power rule in reverse is what can be used frequently to find integrals. The problem with integration is that when you have complicated functions, it is not easy to integrate at all. In other words, if I have this, we don't have a product rule like we did with differentiation. This is the product of a polynomial times a transcendental function, e to the x. Well, integration is about 5 times harder than differentiation. With differentiation, you have a product rule, you have a quotient rule, you have a chain rule. With integration, you don't have all of those rules. So in order to integrate a complicated function like this, you have to use very, very unusual techniques. And there's at least 5 of them that I can think of. But the key thing is that there are some functions that do not have an antiderivative. In other words, that does have an antiderivative. If I take the derivative of that, I get x squared. Right?
Yes.
If I look at a function like this, believe it or not, there is no function in the universe whose derivative is equal to this. In other words, there is no antiderivative for that function. So integration becomes many times more difficult than differentiation. And pretty much integration is all about the techniques you're going to use for integration. Tell me what this is.
Sine x. Yeah, that's the, then you'd have to know the derivatives of the sine code, the trig functions.
Okay. What is the integral of this?
Secant squared x dx equals secant squared, that's The that would be tangent
Very good.
of x.
Uh-huh. In other words, if you take the derivative of that, you get secant squared of x, because the c goes to 0. Okay. So, a couple of things. Let's talk about this for a moment. If you have a constant in your integral, you can remove it and take it outside the integral. If you have a variable, you cannot. So this is a true statement, which then becomes equal to 3x squared over 2 plus c. So as long as you have a constant, you can remove it and take it outside of the integral sign, which is helpful in a lot of instances. If you have this, you cannot remove that. You cannot take that variable outside the integration sign. So these kind of problems become particularly difficult when integrating them.
Yeah.
In other words, how do you figure out what function's derivative is equal to this?
Well, I'm not sure how you would do that.
Well, let's talk about the first method that we would use to integrate besides the power rule. If it's a simple polynomial, you can use the power rule. If it is a complicated polynomial like that, the power rule doesn't really do much good. So we'll use a method called substitution. Let's go through how substitution is going to work here. We're going to let some variable equal x squared plus 1. In other words, the difficult part is what you let your u substitution be equal to. The difficult part being the x squared plus 1 inside the radical. Well, the whole reasoning behind substitution is to turn this integral into an integral that we can integrate. We don't know how to integrate that. But if I let u equal x squared plus 1, look what happens. Du dx is equal to what?
Dx is the derivative of u, so 2x plus
Just 2x, which makes du equal to 2x dx. In other words, we can treat this like fractions. Even though they're not fractions, in terms of operating on differential equations, which is what that is a differential equation, we can multiply both sides by dx and get that. Okay? Now, that makes dx equal to du divided by 2x. Watch what happens when I now try to do this integration. I get the integration of x times the square root of u. Well, dx is equal to du over 2x, so it now becomes that. In other words, I'm substituting for everything that I can possibly substitute for. So now, notice that these x's disappear, and I end up with the square root of u over 2 du. In other words, I've taken this integral that was an integral in x, and I've changed it to an integral in u that I can do. Because this is equal to, I can take that 1/2 outside the integral sign. I now have u to the 1/2 du. Well, I know how to integrate that. What's that equal to?
We have u to the 1 and 1/2 over 1/2.
Over the new exponent, divided by
Over
3
1 and 1.
divided by 3/2, which is the same as multiplied by 2/3. So now notice what happens. I have u to the 3/2 divided by 3 plus c. And what was my u equal to? X squared plus 1. So it's x squared plus 1 to the 3/2 divided by 3 plus c. There's my answer to the original integral. In other words, an integral that I didn't know how to do, this one right here, I was able to do by using this technique called substitution. This is the answer here. Now,
basically just u substitution.
yes, that's exactly what it's called, is u substitution. And what you're going to find is the following, is that integrating functions is at least 10 times harder than differentiating functions. Sometimes you can use the power rule. Sometimes you can use u substitution. Sometimes you can use partial fractions, integration by parts, integration by trig substitution, integration by infinite series. In other words, integration is at least 10 times more difficult than differentiation. We don't have simple rules for integration. We have all of these techniques that work on certain kinds of functions, but they don't work on all functions. In other words, integration by substitution might work on 5% of your functions.
Yeah.
Integration by parts might work on another 10% of functions. Integration by trig substitution might work on another 20% of functions, and so forth and so on. But the problem becomes that it's so much more hard to integrate than it is to differentiate. So you have to learn all of these different techniques. All right, let's see what else is in Chapter 4 here. Let's look at something like this. How can I integrate that?
Would we start by we got the x squared on the bottom, and we have the x plus 1 on top, and we need to figure out what gives us that inverse. could we replace, I don't know, would it be easy to replace the bottom with a U and then...
No, what we want to do is break this up into two integrals. In other words, realize that it's much easier to integrate additions than it is multiplications. Well, if I separate this into two fractions, that being one and that being another, I get this. Well, now I can just apply the power rule to this, because this is the same thing as x to the 1 over x to the 1/2 plus x to the minus 1/2. And both of these integrals can be done very simply using the power rule. What's this part here equal to?
X squared over...
Actually, x to the 1 over x to the 1/2.
Oh, just this thing.
What is this equal to? X to the 1 over x to the 1/2.
X to the 1/2.
Exactly. That's equal to 1 x to the 1/2.
And then the other one is x to the 1/2 divided by...
Well, notice that each of these can be integrated quite easily. What's the integral of this equal to?
The integral of x to the 1/2 is just x to the 3/2 over 3/2.
And the integral of this one?
Is x to the 1/2 over 1/2.
So there's your answer. In other words, by splitting it into two integrals instead of one, I was able to apply the power rule and come up with the answer quite easily. Let's do another one. In other words, this chapter 4 mainly focuses on the power rule and some trig functions. Now, a lot of these you really need to know your trig identities. Turns out that integration uses a ton of trig because there are a lot of polynomial functions that are impossible to integrate. But if we can turn them into trig functions, they're very easy to integrate. So turning polynomial functions into trig functions is a very common technique used to integrate. Now, this one isn't obvious, so let me rewrite it as this.
So then...
What's 1 over cosine? 1 over cosine is what?
Secant.
And sine over cosine is?
Is that tangent? What?
Yes.
Yes, tangent.
And now, what function's derivative is equal to that?
Secant, tangent, that's... secant, right?
Yes. In other words, that's the answer. So a lot of times with integration, it's just turning it into something that you recognize is the derivative of something else. In other words, integration is all about finding the antiderivative. If you were to find the derivative of our answer, you would get secant tangent. Well, that's what we were trying to find the integral of. All right, let me look. Let's talk about slope curves for a second. Do you know what I'm talking about when I say that?
Slope curve?
Yeah. In other words, if we had the integral of x squared, what's that equal to?
3x or x to the third over 3
Plus c.
plus.
If I were to graph that, I would get something that looked like that. Except the plus c represents a vertical shift, right? So my answer could actually be any of these curves.
Infinite number of possibilities.
Exactly. In other words, since c can be anything in the world, then the curves can be all vertically shifted. So that if you were to take the integral of x squared and graph it, you would get something like that, where you would see an infinite number of possible graphs. That's all that slope curves means. It's a difficult concept to understand in calculus. I know I had a lot of problems with it, and that's all that it means. If you understand this, you understand slope curves. Each one of these curves represents a different c. So you basically have an infinite number of them.
So slope curves is understanding that when you integrate a function, the number of curves, it could be like infinitely shifted.
Yeah.
Anyone?
All right. Let's look at the following problem. F prime of x, meaning the derivative, is equal to 1 over x squared, where x is greater than 0. And we want to find the answer to this where f of 1 equals 0. In other words, we know the derivative, we're trying to find the integral, and remember that there's an infinite number of integrals that satisfy this, but there's only one integral that satisfies that. What is the integral of 1 over x squared?
1 over x squared is 1 over x to the third divided by 3.
Well, hold on. Always rewrite these as with an exponent. What's the integral of x to the minus 2?
Integral of x to the minus 2 is x to the negative 1 over negative 1.
Right? Plus c? Okay. So, if I say f of 1 is equal to 0, well, that means when I substitute 1 for x, my answer is 0, so that allows me, this is called an initial condition. And it is what allows you to figure out what c is. In other words, whenever I substitute 1 for x, I get 0. So 0 would be equal to minus 1 to the minus 1 plus c. Well, this is equal to 1, minus 1, excuse me. So c is equal to 1. So the answer to this, in other words, the answer to this integral with this initial condition is exactly minus x to the minus 1 plus 1.
So
that is our function. If I take the derivative of that, I get 1 over x squared. Not only that, but if I want to know what f of 1 is, it's equal to precisely 0. It's not equal to anything else but 0. In other words, I now have a finite number of solutions. Once I put an initial condition on it, it takes away all of those infinite answers. In other words, I had an infinite number of answers to that integral, but the moment I put an initial condition on it, I only have one answer. And that is minus x to the minus 1 plus 1. So the moment you put an initial condition on your integral, then you only have one answer, not two. What's the integral of this?
X.
X plus c.
I
Uh-huh.
really need to remember that plus c.
Yeah, it's hard. Everybody forgets it. And it's only important when you're doing indefinite integrals. In other words, starting in chapter 5, you're going to be doing integrals that go from 1 to 3 or from one number to another number. And then you don't have the c anymore. You can evaluate it specifically. So the only time you have the plus c is when you do not have limits of integration. All right, let's do a vertical motion problem. A ball is thrown upward with an initial velocity of 64 feet per second from an initial height of 80 feet. Find the position function giving the height as a function of time. When does the ball hit the ground? Well, let's do the initial condition. First of all, let's talk about position, velocity, and acceleration. Position functions are usually written this way, s of t. Velocity functions are written this way, and acceleration functions are written this way. This is the first derivative of position. Acceleration is the first derivative of velocity. So acceleration is the second derivative of position. And this is probably the, what do I want to say, the ultimate problem with integration is determining position, velocity, and acceleration. So if I start with the problem, the ball is thrown upward with an initial velocity of 64 feet per second from an initial height of 80 feet. Well, that means the position at time 0 is equal to 80, right? In other words, if it starts from a height of 80 feet, its position on the vertical is 80.
80.
Okay. Well, if its position is 80, and I know that its velocity, which is the first derivative of position, is 64, well, I also know that the acceleration due to gravity is equal to minus 32. In other words, whenever I throw that ball up in the air, I know that gravity is acting on it at 32 feet per second per second. Have you taken any physics yet?
No, I'll be taking physics next year.
All right, well, you'll get a lot more of this. But you're going to get it in calculus also, because this is huge. Position, velocity, and acceleration. All right, so let's start from acceleration. If acceleration is equal to minus 32, well, if I integrate that, I will get the velocity function. So if I take my integral of the acceleration function, I get the integral of minus 32 dt. Everything is in time when we're talking about position, velocity, and acceleration. It's always per seconds or per some other time frame. But what's the integral of that?
That would be negative 32 t squared.
No, just t.
Well, not t squared, sorry, t. Negative 32 t
Plus c.
plus c.
Okay? Now, we know what the initial velocity is. In other words, this is velocity, right? The integral of acceleration has to be velocity. You understand? You get that?
Yes.
The integral of velocity has to be position. So if I'm integrating the acceleration function, which is 32 feet per second down, I get minus 32t plus c. Well, we know what the initial velocity is, 64. So I can set 64 equal to minus 32t plus c. Well, they're saying that the initial velocity is 64 when time is 0. So therefore, c has to be 64 here. So my velocity function has to be minus 32t plus 64. You see how I got that?
Yeah.
In other words, when I set t equal to 0 right here, then c has to be 64. Right. So, in other words, I can work backwards. And then I know that my position function is equal to the integral of my velocity function So my position function is minus 16t squared plus 64t plus c. In other words, I took a straight integral of my velocity function.
Yeah. And we went back to position.
And I also know that because my initial height is 80 feet, remember that the position function is height. In other words, if I want to know the height of this ball at any point in time, I look to the position function, and that'll tell me the height. Well, I know that when I release the ball, it was at a height of 80 feet. So S of 0 is equal to 80. Well, if I plug that in, S of 0 equals 80 equals minus 16 times 0 squared plus 64 times 0 plus C. Well, C ends up equaling 80. So now I have my exact position function. Excuse me, this is 80. Now, it's important to know what's going on here. We have a ball being thrown up like that and coming back down. This is S of t. This is t. So it doesn't really start here at 0. It starts at 80. So I'm really throwing a ball up like that. So if I want to know the height of the ball at any point in time, I can look at the position function. In other words, after about 2 seconds, the ball is higher. And then the ball comes back down, and at some point in time it hits its starting height, and then at some point in time it actually hits the ground.
Yeah.
Notice that the position function merely measures the height of the ball at any point in time. The velocity function measures the velocity of the ball at any point in time. Well, S prime of t is equal to minus 32t plus some c. So this is a super important problem in calculus because it's so common and it's so perfect for calculus, where you have the position function, then you have the first derivative of the position function, which is the velocity function, and then you have the second derivative of the position function, which is the acceleration function. They're all different, but one is just the derivative of the other. So once I've come up with the position function, which I've done by working backwards, this is the precise position function. We can tell that S of 0 is 80. If I wanted to know what S of 1 was, well, it would be minus 16 plus 64 plus 80. So after 1 second, the ball is higher. Well, when does the ball hit the ground?
When the position function is equal to 0?
Not 0. Where did it, the position function started out at 80.
So when it's equal to 80?
When it's equal to minus 80.
Minus 80?
So we have to solve this equation. In other words, yeah.
And then we perform the algebra required on it. So
Yeah, in other words, this just becomes an algebra problem now.
Yeah.
We subtract 80 from both, or we add 80 to both sides, and we get 0 equals minus 16t squared plus 64t plus 160. And then we solve that quadratic equation. And we're going to get, you always get two solutions with a quadratic equation. One of them is going to be positive, one of them is going to be negative. In other words, if I solve this, I got so t is equal to minus 1 or t is equal to 5. Now obviously t can't be equal to minus 1 because we're talking about time. It's a little bit like working with dimensions. You throw out your negative answers. There's no such thing as negative time. So the only answer that we're interested in is the t equal 5, which tells us that after 5 seconds, the ball will hit the ground. Okay? All right, let me look at the rest of this chapter here. Let me look at some exercises at the end of the chapter. Let's talk about differential equations. A differential equation is any equation that has differentials in it. And you can't have just one differential. You have to have two. In other words, I cannot have this. That's impossible. That makes no sense whatsoever. You can only have differentials if you have a pair of differentials. Now, to solve this differential equation, I'm going to do this. I'm going to put, in other words, I'm going to treat the differentials like they were fractions, multiply, then I'm going to integrate both sides. That rule in algebra that says you can do anything you want to one side of the equation as long as you do it to the other applies to integration also. In other words, you can integrate one side as long as you integrate the other. Well, what's the integral of the left?
The integral of the left, we have y.
Integral of the right? When you're integrating using the power rule, the first step, add 1 to the exponent and divide by the new exponent. That's it. So what's the integral of 3t squared?
We would have just t to the third.
Because it's an indefinite integral, we have the plus c. So we just solved a differential equation. That's the answer. Now, we didn't have an initial condition with this. Had we had an initial condition, we'd be able to solve for c. But we did not. So we have an answer that has c in it. In other words, we have an infinite number of answers. Just give you a couple of more problems here.
Well, it's
I know. I'm just going to give you one or two more. How would we do this one?
cubed root of x squared. Replace x squared with a u and then do it.
Let's turn, whenever you see a radical sign, get rid of the radical sign. In other words, turn this into a function with just an exponent. What's the exponent?
X to the cube, so we would, 2 to the third.
Now you can use the power rule.
We would have x to the 5/3 over 5/3. Plus c.
All right, that's probably a good place to stop. That pretty much, I just realized that's only chapter 4.1. So everything we did today was just 4.1. We haven't really got into the rest of chapter 4 yet.
Okay.
But we will next Saturday.
Yes, and next Saturday I should have actual questions.
Okay.
We'll have started, but
that always works a little bit better. It's better that you bring the problems to the table rather than me, just because I don't always bring the exact problems that you're working on. So. All right, Chase. I will talk to you next Saturday.
Talk to you next Saturday.
All right. Bye-bye.